Now let's dive into the distribution code to take a look at the context in which the code you write is going to be operating. At the end of the day, you're going to implement the entirety of the web server, but we have provided you with this skeleton code that has some functionality, particularly related to networking. Let's take a look. So up here toward the top of the file is a bunch of feature test macro requirements. Now this is just a feature of C whereby according to a bunch of man pages, you have to define some of these constants to be true or to be even specific numbers so that you have access to certain functions. Otherwise, they'll be undeclared and you won't have access. So I've done this by way of reading the man pages. Now down below in lines 15 through 17, we have a whole bunch of limits declared, and we've borrowed these from a popular web server called Apache. And these are just numbers that are going to cap the total number of bytes that are allowed in various contexts for the HTTP requests that a browser is allowed to send me. Next, we define octets. Now, an octet is just a fancy way of saying a byte or 8 bits. It turns out in yesteryear, a byte wasn't necessarily 8 bits, so octet is always 8 bits. So in this case, we've adopted what's common in the networking world of calling 8 bytes an octet. Here, I've specified that octets will be 512, so that much like in forensics, when we read a bunch of bytes at a time, here too, we're going to read a bunch of octets at a time. Next, a whole bunch of header files. How did I know to include these? Well, I simply read the man pages for a number of functions that we'll use in this distribution code and included the ones I was instructed to. And now we have a data type. We've declared an octet to be a char, and we'll see later that that's used throughout the code. And we've declared a whole bunch of prototypes, and we'll walk quickly through each of those functions. Lastly, and perhaps most important to keep in mind at this point in the story, is that there are in fact a whole bunch of global variables at the top of the file: root, CFD, SFD, request, file, and body. Now generally using so many global variables or global variables at all isn't the best practice, but it turns out we're also using a technique called signal handling later in the code, which allows us to detect when the user hits something like Control-C and shut down the server gracefully. And in order to do that gracefully and actually free up memory, we need to have access to these global variables. And now let's take a look at main, which drives the entirety of this program. First, at the top here, we have an error number variable that appears not to have a type, but that's because it's actually defined in a file called errno.h, which is included higher up. If you do man errno to actually see the definition for this thing, you'll see that this is a special global variable that is set by a whole bunch of functions, not written by us, but by the authors of Linux and other systems, to actually set a number to that variable when something goes wrong so that you can globally figure out what did go wrong. Now down below, you'll see a new technique perhaps using getopt, a function that helps parse command line arguments so that we don't have to bother wasting time figuring out how to parse something like 8080 or -p or -h to get help. Getopt essentially does that for us. See the man page for more. Next, we do a bit of error checking to make sure that the port number is within the specified range in the spec. Next, we see a call to the function start, whose definition we'll look at in a moment. And as its name suggests, this starts the web server. Here, we have a call to a function called signal, which says if and when you hear Control-C from the user's keyboard, go ahead and call a function called handler that's going to ultimately clean things up and stop the server. Below that is what appears to be an infinite loop, the first line of which effectively is a call to a function called reset, which we ourselves implement later on in order to free up some of our global states. After that is a line of code that conditionally is checking the return value of connected. Now, connected looks like a predicate, something that returns true or false, and it does, but there's something special in connected in that it's a blocking call. It will sit there and wait until a user's browser tries to connect to this web server, and only then will it return true or false so that we proceed to the inside of this if statement. Once there, notice this function to a function called parse, which we wrote, which parses all of the octets, all of the bytes coming from a browser to the server so that we can hand you back ultimately a value to one of those global variables that stores all of the bytes in just the headers of that request, not the body if there were actually a body to it. Now down below, we begin to parse those headers to extract a subset of the information that we care about. Specifically, per the specification, we first want its request line, which is just that very first line that hopefully says something like get, slash, or some path, and then HTTP 1.1. We're using this metaphor of a needle in a haystack to look for particular chars or addresses. And indeed, there's a number of functions in our distribution code that you too might find helpful when looking for particular values. Ultimately, we copy these bytes into a variable called line, which, notice too, we've allocated on the stack by way of a dynamically sized array, and we're deliberately trying to avoid calling malloc because, again, because of Control-C being a potential feature of this program, we don't want to have this code suddenly interrupted by the user hitting Control-C, the result of which is that I might not have a chance to freeze something I've malloced. So I'm trying to use as much of the stack as I can here. Next up, a whole bunch of to-dos. The specification will expound on exactly what's expected here, but the comments give you a hint of what lies ahead. You first need to validate the request line and make sure that it looks like the specification's grammar, so to speak, says it should. You then need to extract something called the query, the stuff after a question mark, like we saw with our Google example when passing in an HTTP parameter. We then concatenate together the root of the web server with the path that's in that request first line and form the full path of the file we want to look for. Thereafter, we're going to make sure that the file exists and is readable, and then we're going to extract its file extension, the .html or the .php or some such extension that's at the very end of the string requested. Next up is a whole bunch of code we wrote to actually generate PHP-generated content for you. In a nutshell, this code takes in the name of the file you want PHP to interpret. We pass it by something called a pipe into PHP's interpreter, get back the response as though the response were a file itself, and then we iterate over that file's bytes, pulling them all into one buffer so that we can ultimately print them out. Indeed, all of these calls here to dprintf allows us to print to something called a file descriptor, which is just an integer that represents a file. Very similar in spirit, but fundamentally different from a file star pointer. Notice how you can use syntax like printf here so that I can dynamically insert something like length for the value of an HTTP header called content length. And ultimately, I use the function write to actually write the body to the request. Unfortunately, we only implemented support for dynamically generated PHP files. We did not implement support for static files like GIFs and JPEGs and CSS and HTML files. That, unfortunately, is left to you to respond to the client per this to-do. So in there, you'll find that there's not much inspiration within that block, but if you look a little higher up at how we went about interpreting PHP code, the functions you'll use are a little different. In fact, you can borrow some of the functionality perhaps from the forensics problem set, because at the end of the day, all you need to do here is once you know what file to open and once you know its so-called MIME type or content type, you need to read in those bytes and somehow spit them back out. And now a tour of this file's other functions. Up first is connected, which simply returns true when it finally hears a connection from a user. Next up is error. Error, meanwhile, is a function we wrote to handle all of the different 400 and 500 HTTP status codes that you might want to send back to the user, along with a standard message. Next up is load, a particularly meaty function whose purpose in life is to read from a file star pointer the contents of a file into a global buffer that we declared globally above main. This is a bit complex because we have to read the bytes from the file, but check on each iteration whether we've already hit the end of the file or something else has gone wrong. And we use realloc to make sure that whatever buffer we're using is growing and growing and growing and always staying ahead of the number of bytes that we need to fit in there. Handler, meanwhile, is the function that gets called by way of having registered Control-C as a signal that we want to intercept. Notice here in handler that it ultimately calls stop, which of course stops the web server. And unfortunately, lookup is not implemented. In spirit, this is a fairly simple function. Given a file extension, it needs to return its so-called MIME type or content type, and we specify in the specification what that mapping must be, but you need to translate it ultimately to C code. Next up is our similarly meaty function called parse, whose purpose in life is to read not from a file, but from a network connection, specifically reading in and parsing the HTTP request that's come from a browser to the server so that ultimately we can parse out just the headers and the request line and return those to you by way of a global buffer that we declared above main. Reset, meanwhile, is a function that we define that gets called iteratively inside of main every time you're about ready to start listening for a new connection so that we always know the state of our variables and so that we've also freed any memory that might have been allocated for a previous network connection. Next up is start, the function that we wrote that contains a whole lot of networking code that ultimately starts the web server. Last up is the function called stop, which does exactly that. It stops the web server. But first, it frees up any memory that still has been allocated, but it ultimately calls exit without even returning control to our main function. Ultimately, one of the most important techniques when implementing this web server is going to be a bit of trial and error, having one browser window open at right and a terminal window at left, the server's console window, so that you can see the messages that are being displayed on the screen. But better still would be a third window, a second terminal window in which you use Telnet, the usage for which is prescribed in the spec. And Telnet is just a very simple network program that lets you to pretend to be a browser in one window while talking to the other window. This way you can see exactly the textual commands that are coming back from server to client without having to poke around Chrome's developer tools and an otherwise clunkier interface.